Question 10 of paper 2, June of 2024. In the diagram, the line COD is the diameter of the circle with center O. EA is a tangent to the circle at F. AO is perpendicular to CE. Diameter COD produced intersects the tangent to the circle at E. OB produced intersect the tangent to the circle at A. CF intersects OB in T. CB, BD, OF, and FD are drawn. 10.1. Prove with reasons that TODF is a cyclic quadrilateral. So let us mark TODF on our diagram. And what I notice is that the exterior angle of that quadrilateral is equals to 90 degrees, and that was given in my information. So if I can prove that the angle of O1 is equal to the angle of F3 and 2 together, then I'll have exterior angle of a cyclic quad, and that will make TODF a cyclic quadrilateral. Now this angle of F2 and 3 is part of an angle at the circumference, and in that triangle we have the diameter as well. So we know that F2 and 3 together is 90 degrees, angles in a semicircle. So for 10.1, we can say O1 is equal to 90 degrees, given. Then we can say angle TFD is equal to 90 degrees, and that is the angle in a semicircle. So TFD is the angle of F2 and 3 together. Therefore, O1 is equal to the angle of TFD, and therefore TODF is a cyclic quad. And because we are proving something, we need to have a reason. So what we have proven is the converse or the reverse of the exterior angle of a cyclic quad. So remember that when you prove a cyclic quadrilateral, you need to state a reason why that statement is true. 10.2. Prove with reasons that D3 is equal to T1. So let us mark angle D3, and we want to prove that it's equal to angle T1. So in the previous question, we have proved that TODF is a cyclic quadrilateral. Now you can use that statement to make angle D3 equal to angle T3. And you can say D3 is T3 exterior angle of a cyclic quad, and you can see that T1 and T3 are equal vertically opposite angles, and therefore D3 would be equal to T1. So let's write down that solution. We can say D3 is equal to T3, the reason, exterior angle of a cyclic quad. Then we can say the angle of T3 is equals to the angle of T1, and the reason is vertically opposite angles. Therefore, the angle of D3 is equal to T1. 10.3. Prove with reasons that the triangle TFO is similar to the triangle DFE. So let's have a closer look. So the triangle of TF and O, we want to prove that similar to the triangle of DF and E. So in my previous question, I've proven that T3 is equal to D3. Then all that I need to do is either find O2 equal to angle E, or I need to find angle of F4 equal to angle F2. Now what I notice here is that F4 is connected to a tangent and a chord. So I know that the angle of F4 would be equal to the angle of C2. And can you see that the angle of C2 is part of an isosceles triangle? So that means that C2 would be equals to F2. So therefore we have F2 is equals to F4. And then our last angles we don't have to prove. So let's write that solution formally. We would say in triangle DFE and triangle TFO, we have D3 is equal to T3, and we have proven that in our previous question. Next, we can say that the angle of F4 is equal to the angle of C2, and we are using the tan chord theorem. And we can say that C2 is equal to the angle of F2 because those are angles opposite equal sides. And we can conclude then that F4 is equal to F2. Then for our third statement, we can say that the angle E is equal to the angle of O2, and you can say third angle of triangle, or sum of angles in a triangle. Therefore, the triangle DFE is similar to the triangle of TFO, and we need to write down a reason of angle, angle, angle. 10.4. Prove with reasons that if B2 is equal to E, that DB is parallel to EA. So let's mark those equal angles. So they say that B2 and E are equal. And what I notice is that one of the arms connected to the angle of B2 is the radius of the circle. And that forms part of an isosceles triangle. So I can say that B2 is equals to D1. And if B2 is equals to D1, then we have D1 is equals to angle E. And then we have proven corresponding angles equal. So let's write down that solution. We can say that angle E is equal to angle B2. That information was given in the question. Then we can say that B2 is equal to angle of D1, and those are angles opposite equal sides. Therefore, D1 would be equal to angle E. Therefore, the line of DB is parallel to the line of AE, and what we have proven is corresponding angles are equal. Notice that we don't say corresponding angles equal with our parallel lines at the end of the statement. We are proving that those lines are parallel, and the reason why they are parallel is because the corresponding angles are equal in size. 10.5. Prove that DO is equal to TO times FE divided by AB. So let's inspect our sketch. We want to prove that DO is equals to TO times FE divided by the line AB. Now what I recommend you do is that you mark each of these sides on the diagram. So I'm going to highlight them. So we have DO, then we need to look at TO, FE, and AB. So it looks a little bit like the sides are not connected at all, but let's use what we've proven in the previous questions. So in the previous question, we've proven that DB is parallel to AE. And also what I can see is that the triangles that I've proven similar, I've also marked. So I know that if these triangles are similar, that the proportion of TO and DE would be the same as well. And the other thing that I notice is that the line of DO is connected to a triangle with parallel sides. So I'll probably use the proportionality theorem. So maybe let's start with that. So I can say that DO over DE is equal to OB over AB. And the reason is line parallel to the side of a triangle. Obviously, we want to find DO, and I already have the AB in my denominator. So can you see that DO can be written as OB times DE over AB? So we already have the denominator of AB. Next, I'm trying to find a way to connect TO to either OB or DE and FE to either OB or DE. Now I am mindful that this might turn into a ratio as well. So at the moment, I don't want to work with OB because it's not connected to anything that I've proven before. But I see that DE is connected to the similar triangles that I've proven in a previous question. So I know that DE over TO is equal to FE over the O of F, and this is from the similar triangles. So from the similar triangles TFO, which is similar to D, F, and E. So what I'm doing is I'm saying DE over TO is equal to FE over O of F. And that's from the similar triangles. So I'm creating that ratio. So therefore I can rewrite DE as FE times TO over OF. So can you see in our ratio we have DE now. So let's rewrite that information in our ratio. So we have DO is equal to OB times DE, where we're replacing that DE with FE times TO over OF. So it will be FE times TO over O of F over the A of B. So all that I'm doing is I'm writing DO again. I still don't have OB, but I've rewritten DE. And what I want you to notice is that the O of B is a radius, and the O of F is a radius as well. Therefore, we have the O of B is equals to the O of F. Those are radii. That means that the radii would cancel each other out, and therefore DO is equals to FE times TO over AB. And that is what we wanted to prove. Thank you for watching. Remember to show your support by hitting the like button and subscribing to Mathenatic.